coated nickel reduction. The authors are Steve Robb and J.A. Locher, both of Technische Universität Vienna, and also the Professor Goodwin of the University of Pittsburgh. The paper will be presented by Professor Goodwin.
Okay, as mentioned in the introduction by Dr. O, I'd like to call attention to my collaborators, Kristen Robb and Johannes Beckner of the Technical University of Vienna. There's a lot of interest in promoting the reduction of base metal catalysts. You can see this both in terms of a number of papers in the literature, not a huge numbers, but also a lot of patent activity in the last 4 or 5 years. There are certain obvious reasons why you might like to promote, let's say, the reduction of base metals. Typically, supported base metals especially have a very high temperature required for reduction, greater than 500 degrees centigrade often. And such high temperatures can easily result in such deleterious effects as sintering of the metal, initiation of SMSI or other types of metal support interaction, destruction of metastable metal surface structures that may be derivable at low reduction temperatures, as well as possible phase changes in dealing with some of the new novel supports being tried out and utilized. It's been known, certainly for quite a number of years, that a small amount of noble metal, when added to a base metal, can greatly decrease the temperature required for reduction at any sort of reasonable rate. The nickel-platinum system is of interest for a number of reasons, which make it sort of a model. One is that it's the nickel and platinum are totally miscible for all compositions. The second thing is that their precursors reduce something on the order of 200 degrees centigrade apart, and therefore have significant differences in ease of reducibility. Unalloyed nickel can be characterized effectively by magnetic measurements, and the catalytic properties, if one is investigating the nature of the surface of this bimetallic system, the catalytic properties of pure nickel and pure platinum are quite significantly different vis-a-vis CO hydrogenation, paraffin hydrogenolysis, among other things. And finally, it's certainly an effective model of many bimetallic catalysts for selective hydrogenation. I'm not going to spend much on the background of this system because of the time limitations. But one thing that I will mention from the large number of surface science studies which have been done on nickel-platinum alloys, and that is that it is well known that in nickel-platinum systems you can get surface segregation of platinum when you have nickel-platinum alloys. And I'll come back to that vis-a-vis supported items. There's been one paper in the literature that I know of, perhaps I'm missing someone, I'm sure it will be pointed out if I have missed it, but this is a paper, a very nice paper, about 2 years ago by Professor Kurz, and this was for nickel platinum on silica, and among other things they looked at, for about 28% nickel, a system with a little bit of platinum in it, and they saw basically that the reduction temperature, there was some perhaps increase in reducibility, though it wasn't very clear based on the amount of platinum that they were adding. This being obviously nickel, the reduction peak for platinum being somewhere down here, and they were following the reduction of the precursor as opposed to the reduction of the calcine catalyst. In our investigation of this promotion of the reduction of the nickel, we used the nickel chloride, platinum chloride, used the Degussa silica, and we had two series that I will briefly mention. One is Series A, which has a constant number of metal atoms on the surface in terms of 400 micromoles of metal per gram of catalyst, prepared by an incipient wetness using co-impregnation. And Series B, which was a constant weight loading of 5 weight percent, which was an earlier study, which was wet impregnated, but the type of preparation, there could have been some ion exchange going on simultaneously with that. We used a wide variety of techniques, including TPR of the catalyst precursor, TPR there oxidized reduction catalyst, as well as chemisorption, XRDT, etc., and also some reaction studies. I'll briefly mention some of the seal hydrogenation results here. Basically, from this system, this is the results from hydrogen chemisorption, and you'll see that as you go down, this is 100% nickel floating down to 0, and a concomitant 100%, that is not in weight percent, but in terms of the 400 mole micromoles, 100% of it being platinum down here. And the first thing that is noticeable is that very little effect on dispersion and on particle size for this system until you get down to the pure platinum, and that's a little higher dispersed, but more or less it's around 18 to 20% dispersion for all these elements. If you look at just the reduction of the precursors, this is reduction of nickel chloride somewhere around 750 degrees or so. Reduction of platinum chloride in the bulk state can occur around 400, 420 or so. And if you put take a pure nickel or pure platinum catalyst and or nickel precursors on silica, platinum precursors on silica, you get some change in the reduction point of this precursor, but you see that they are still quite separated, one from the other. When we put nickel and platinum together on the surface, or I should say nickel chloride and platinum chloride, this is the pure nickel case, pure platinum case, and you'll see a reduction here, reduction temperature somewhere around 530 degrees, in which by that temperature all of the platinum is completely reduced. For nickel, you'll see a reduction temperature around 722 degrees Kelvin, at which time, more or less, most of it gets reduced by a little higher temperature than that. Now, in between, where of course the interest lies, we've got everything from 10% mixture to 90%. And basically, you see is that as you add a small amount of nickel platinum chloride to the nickel chloride on the support, you see a reduction in the temperature required to reduce the nickel. The interesting thing to note is that there appears to be no effect of the nickel chloride on the reducibility of the platinum chloride. That's all occurring within experimental error at this point right here. But as you add from 10, 20 to 30%, the temperature for reduction of nickel gradually approaches that of platinum, and by the time you get a 50-50 mixture, you have identical reduction temperatures of the precursors. This is also seen with the other series of catalysts, which is a somewhat different preparation method, suggesting that this effect is not strongly an effect of the method of preparation. There are some differences here, probably because with this system there was not only a sort of impregnation, a wet impregnation, but also some ion exchange that may have occurred. But qualitatively, the results are identical, suggesting, as I said, the method of preparation is less dramatic. If you take these reduced catalysts, reoxidize them in air at 673, and then do another temperature program reduction, what you see now is that you don't see the big differences between the reducibility of the nickel and the platinum. You are obviously getting, there's a shift from the pure nickel as you go towards the pure platinum. There's probably not even total bulk oxidation of the maybe of the platinum, but and certainly very easy to reduce at very low temperature. If you look at the XRD results, because we're dealing with something like 50 or so angstrom particles, in the series A, you can clearly see 100%. We're seeing reflections from the standard nickel planes. As we go to lower weight or lower fraction of nickel, we lose the ability to see it, and in fact, for using magnetic measurements, we cannot detect any pure nickel phase below somewhere between 50 and 70% of the catalyst being nickel. We do see some nickel, we see for the series A, which is a sort of pure state, we see nickel NiPt phase formation in the intermediate ranges, and then of course we see platinum, pure platinum, down from 50% all the way down to 0. In the series B, it's a little more complicated system, and we actually get some nickel-3 platinum or reflections from nickel-3 platinum 111 bases. If we look at the surface of this catalyst by zerohydrogenation, we get a tremendous fall off in turnover frequency as we go from the pure nickel system towards the pure platinum system, as you'd expect. This would be maybe what you'd expect if you had an ideal mixture, that is, the surface being the percent nickel that you would expect from the bulk. If you then take this and use this to come up with some quasi-determination of surface composition, then it would suggest this, that as you increase the amount of platinum in the system, there is a very quick enrichment of the surface in platinum, which certainly fits what one sees with the single crystal studies of the bimetallic phases. Finally, conclusions, metal dispersion is not greatly affected by the presence of platinum. It doesn't decrease or anything like that, the dispersion of nickel. Reduction temperature of the platinum is not affected. I'm talking about platinum precursor now. However, the reduction temperature of nickel is greatly affected, and for about greater than 30 mole% platinum, you can, of course, reduce the nickel at the temperature of platinum. Of course, I'm talking kinetics here. Obviously, you could, I'm sure, without a program, you would reduce it over some hours at the lower temperature. XRD indicates that there's certainly pure nickel phases present at the high concentrations of nickel. There's certainly pure platinum phases at over quite a wide range of the system. And we do have definite alloy formation between the nickel and platinum. There is surface segregation of the platinum, which suggests that if one is trying to achieve a catalytic properties of the base metal, perhaps you would want to concentrate on something which does not segregate to the surface, because obviously you're getting less and less of the nickel surface character in these systems. In adding a noble metal promoter to a base metal system, if you're trying to achieve a better base metal catalyst, you would probably want a noble metal which preferentially stays in the bulk of the particle and does not preferentially segregate in order to prevent deleterious effects on the reaction properties. Finally, I'd like to acknowledge Stefan Azteca, who did the Catalyst Series B, as well as government support from the government of Austria and Department of Energy Basic Energy. I thank you.
Any questions?